Okay, so our next speaker is John Ellis from King's College and CERN, and he's going to talk about Higgs physics and cosmology, I believe.
Yeah. Does this advance the work? So I regularly offer a small prize for whoever knows where this picture was taken, but don't think anybody's actually won it yet. Sorry? No. Okay. So my job is to somehow make the connection between what you just heard from Lars and cosmology, which is the main interest of this group here. And I'm going to obviously talk quite a bit about the Higgs boson, but not exclusively. I'll also talk about supersymmetry, and I'm going to try to make the connection with inflationary cosmology also. So I should start with this. This is the papers that were published back in 1964 about electroweak symmetry breaking, and in particular predicting the existence of a Higgs boson. I'd like to draw people's attention, by the way, to this paper here, which actually came out the following year, 1965. Paper written by two 19-year-old Russian theorists, Migdal and Polyakov, which actually did a very complete job on the Englert-Brout, Higgs, Guralnik, Hagen, Kibble mechanism. And the publication of their paper was delayed for quite some time because the old farts of the Russian Academy couldn't believe that two 19-year-olds would come up with something so fundamental. Anyway, so with all these people who came up with this idea for giving masses to elementary particles, you might be forgiven for wondering, well, why is it that we call it the Higgs boson? And the answer is because of all these people, Peter Higgs was the only one who actually mentioned the possible existence of a massive scalar particle. So that was back in 1964. My own interest in this started back in 1975 when I wrote this paper with Mary Gaillard and Dimitri Nanopoulos. And at that time, this whole thing was extremely speculative. Nobody was taking the thing seriously at all. Nobody had any idea what the mass of the Higgs boson might be. And for that reason, we wrote at the end of our paper, we don't want to encourage big experimental searches for the Higgs boson. Fortunately, our excellent advice was not taken by the experimental colleagues. So Lars has already shown you a lot of data on the Higgs boson. I can tell you this is a very exciting moment for us particle physicists, in particular Peter Higgs, who seems to be trying to calm his heart palpitations. Okay. So, as Lars has already told you, experiments looked for the Higgs boson over a large range of masses. So I'll show you an unofficial compilation of the data as they were on March of this year. They haven't changed very much since then. You see, nothing very much over a large range of masses. But then here, when you take away the blind, you see this very significant peak, which is, I know what it is, 11 sigma, 12 sigma, something like that, indisputable. And we'll believe it's the Higgs boson, but of course, this needs to be checked. So Lars told you a little bit about some of the checks that have been done. I would compare the situation to you've been doing this particle jigsaw puzzle for 49 years, and you finally found this bent piece of cardboard in the back of the sofa, and the picture's rubbed off. And the question is, does it have the right shape? Does it have the right size to be the Higgs boson? So the right size, in my book, translates into the question, does this thing have the same coupling strengths as what you would expect for a Higgs boson? So Lars has showed you some individual data from Atlas and CMS. This is a compilation that I did with my PhD student, Tivong Yu, where we combined the data from the LHC experiments and also from the Tevatron experiments in the various different channels that Lars mentioned, decays into BB bar, tau tau, gamma gamma, WW, ZZ, and so on, and this is the combined thing. So if you can read it, it says that combined, the overall signal strength is 1.02 plus or minus something like 0.12. So this thing very much resembles a standard model Higgs boson, and I'm sure Peter Higgs is smiling at least until the Nobel Prize announcement in October. So, Tivong, you and I also display the impact of all these various different measurements in a plane which represents the couplings to bosons and to fermions, so that the fermions are the vertical axis C, the bosons are the horizontal axis A, and the little green star represents the standard model prediction, and the various different observations constrain these parameters in various different ways. If you put everything together, this is the final global combination, and the little bright spot here, this is what the data are telling you. The data are telling you that this thing really does resemble a standard model Higgs boson. These yellow lines, by the way, these are sort of rival theories, composite models, whatever. Well, some of those models are compatible with the data, but if and only if they look extremely much like the standard model Higgs boson. So with Tivong, we also looked at the data in a somewhat different way. So it's absolutely crucial that the Higgs boson should couple to other particles proportional to their masses. So we did a fit where we looked to see whether the couplings are proportional to mass to the power 1 plus epsilon with an overall scaling parameter which might not necessarily be the conventional electroweak scale. And so the standard model corresponds to epsilon equal to 0 and a scale of 246 GeV. That's the red line there. And you can see the data are in mind-bogglingly good agreement with that. The fit that we get is this dashed line here with a dotted line for the 1 sigma excursion. So on the strength of that, we wrote in one of our papers that this particle certainly walks and quacks like a Higgs boson. Okay, so that's the good news. On the other hand, there are a lot of dogs that did not bark, and Lars showed you an impressive collection of various different searches for new physics at the LHC, which so far haven't found anything. I don't know whether people still read Sherlock Holmes. If you read the story about Silver Blaze, and the most important clue there is the dog that did not bark. And this is a typical conversation between Sherlock and some stupid policeman. Anything else you want to point out to me? Well, there's a curious incident of the dog in the nighttime. Policeman. But the dog didn't do anything in the nighttime. That was a curious incident. And so, we're somewhat in the same situation here at the LHC. The Higgs boson has appeared, but we haven't yet found all the other physics that we theorists have been speculating about for decades. Maybe you cosmologists can help us out on that. So let me fill out this point in a little bit more detail. So the LHC has shown us a relatively light Higgs boson, weighing about 125 GeV, but nothing else up to, as you saw in Lars's talk, TeV energies. So the question arises, if there is something else light, why haven't we seen it? For example, Lars mentioned this extremely rare decay of Bs into mu plus mu minus. This is something where many theories predicted that there might be something beyond the standard model showing up, but nothing did show up. Looks very much like the standard model. On the other hand, if there is nothing light at all, then it becomes problematic to understand why the Higgs boson has this sort of mass gap relative to all this other new physics. And this is often phrased in terms of very simple perturbative diagrams, like these here. You write down one loop diagram, and if you calculate that in the standard model, you get an enormous contribution. And if you want to get a relatively light Higgs boson, it has to be cancelled out by something new. That would seem to require additional physics, some new approximate symmetry, and nothing of that sort has shown up so far. So that's the puzzle that we have. Now I said that the dog has not barked. Well, maybe the dog hasn't barked, but there has perhaps been a little bit of a sniffle from some dog. So let me come back to the measurements of the Higgs mass and the top quark mass that Lars mentioned in his talk. So Higgs, as I mentioned, is a very delicate object. And one of the aspects in which it's delicate is that if you try to extrapolate the standard model up to high energies, there's a danger that the Higgs coupling might actually blow up. Now, that would have happened if the Higgs mass had been too large. In fact, of course, the Higgs mass is relatively small. In that case, another catastrophe happens, which is that the renormalization by the heavy top quark that Lars told you about could actually drive the Higgs self-coupling negative, and this introduces an instability in the electroweak vacuum. And this instability is calculated to set in somewhere around 10 to the 10, 10 to the 13 GeV. So this is perhaps the first interface with cosmology. If you take this seriously, the measurements of M Higgs and M top, and if there's no new physics, our current vacuum is unstable, and the universe will descend into a big crunch sometime in the future. Unless, of course, we have some new physics, such as supersymmetry. I'll come back to that later. So this is a little bit more detail on this. Maybe we just focus on the right-hand picture here. So horizontal axis M Higgs, vertical axis M top. The green region, that's the stable region. Nothing for your grandmother to worry about. This yellow region here, this is where the vacuum is in principle unstable, although the lifetime will be very much longer than the age of the universe. And the current indications are that we're living in this unstable region, which is maybe bad news for your grandmother, but it's good news for us particle theorists. So how would you set about stabilizing this electroweak vacuum? What sort of new physics would you introduce? So this instability, I remind you, is driven by a heavy fermion, the top quark. So let's put in a heavy scalar and cancel it out. Well, that's fine, but then you get the same problem all over again, that the coupling might either blow up or it might collapse. So you better put in some new physics to stabilize that as well. And I studied this with Douglas Ross a few years ago, and we finished up with a theory which looked very much like supersymmetry. So that's one of the reasons why whenever I'm asked what else is there out on the particle physics horizon beyond the Higgs boson, I respond supersymmetry, and I've written supersymmetry in the largest possible font that fits on the slide. So actually, I would say that the discovery of the Higgs at the LHC has given us at least two additional reasons for liking supersymmetry beyond those that we had before. There's the successful prediction for the Higgs mass. Supersymmetry predicted that it should weigh less than 130 GeV. There is a successful prediction for the Higgs couplings. In the sort of typical sort of supersymmetric theory that we're talking about, the coupling should be within a few % of the standard model values. And all of this, of course, is in addition to all the traditional arguments, the sensitivity of the Higgs mass that I mentioned earlier on, and of course the fact that it could explain the dark matter in the universe. So, lots of nice reasons for believing in supersymmetry. On the other hand, as I think Feynman once said, if you had one very good reason, you wouldn't need to quote lots of reasons. Okay, so let me talk a little bit about supersymmetric dark matter, although Malcolm Fairbairn, replacing Stefano Profumo, will talk about dark matter in more detail shortly. So in a supersymmetric theory, many supersymmetric theories, there is a conserved quantum number which guarantees that the lightest supersymmetric particle is stable. This is first pointed out by Fayet back in the 1970s. So this multiplication of the conserved quantum number tells you that sparticles should be produced in pairs, heavier sparticles decay into lighter sparticles, and this of course means that the lightest one, since it doesn't have a legal decay mode, could be around today as a relic from the Big Bang. So this is a relatively generic feature of supersymmetric theories. Let me just show you what happens in the simplest possible supersymmetric theory, just as a sort of representative of that class. So I assume here that the lightest supersymmetric particle is a supersymmetric partner of some combination of photons and Higgs bosons and Z bosons. And there's a bunch of constraints there in brown, green, and pink, which come from various different accelerator experiments. Let me not go into the details of those. There's a constraint coming from the LHC, the fact that, as Lars told you, we haven't seen supersymmetric particles there yet. And then there are regions of parameter space where you can get the right dark matter density. So in this particular model, there's a strip along here, another strip along there. You might say, well, those strips look very thin and narrow, right? And this looks like it's kind of fine-tuning. That fine-tuning is the responsibility of you, our dear cosmological friends. And in particular, it was the WMAP experiment, which gave a fantastically tight constraint on the relic density, which meant that only a small fraction of any model's parameter space would give you the right amount of dark matter. So this is another example of a supersymmetric parameter space, which in this case, the WMAP and a Planck-compatible region looks a little bit more impressive. So as Lars has told you, LHC experiments have looked for dark matter. In particular, they look for events with missing energy carried away prospectively by dark matter particles. It's actually a relatively generic search, although I'm going to look at it in the context of supersymmetry. And this is an event observed by CMS, so lots of stuff coming out the top part of the detector, nothing visible coming out the bottom part of the detector. Just exactly the sort of thing which we would love to see. Unfortunately, this is completely compatible with the standard model. No evidence for anything beyond. So Lars already showed you somewhat subliminally a compilation of the various different LHC constraints. This was how they were in the middle of last year. This is how they are now. So lots and lots of searches, as he's told you. There's a couple of different supersymmetric mass scales, one on the vertical axis, one on the horizontal axis. If you can read what's written here, it's telling you that squarks and gluinos probably weigh more than 1 or 1.5 TeV. So with some of my colleagues from Imperial College and elsewhere, we've been trying to compile all the constraints on supersymmetry. And so again, this is the unseen scalar mass scale, the unseen fermion mass scale. Green star is the best fit point. Red region, those are 68% confidence level regions. Blue, that's 95% confidence level. So that was actually before the very latest Atlas constraints that Lars showed you. This is actually where the Atlas constraints would fit in this plane. So we haven't actually done a global fit, including these latest data yet. That's in arbite, as the saying goes. But you can see that that's going to shift things up a little bit, but not dramatically, I don't think. So what does this actually mean in terms of possible supersymmetric particle masses? For example, the gluino mass or the dark matter particle mass. So this is the result of our fit for the gluino mass. And bizarrely, we actually find a couple of relatively favored regions. I emphasize again, this isn't the simplest possible model. And one of these regions, the region on the left, I think has every chances of being explored with the upgrades of the LHC that Lars mentioned. On the other hand, the region on the right, this would actually require a higher energy accelerator. And so if we still believe in supersymmetry 10 years hence or so, then maybe that will provide additional motivation for going to the very high energy LHC. Okay, so there's certainly plenty of connections between supersymmetry and cosmology, assuming that supersymmetry exists at all. And one of them I already mentioned is dark matter, and Malcolm will be saying more about dark matter in a moment. I actually wanted to spend the rest of my talk talking about connections between supersymmetry and cosmological inflation. So we'll be hearing a lot about this later on in the meeting. So I don't need to tell you that the Planck CMB observations are nicely consistent with the generic idea of inflation. There's a tilted scalar spectrum, which is certainly redolent of rolling down some potential towards eventually zero. On the other hand, here again, there's a dog that did not bark. In this case, the dog that did not bark was tensor perturbations, which now have an upper limit of something like 10% of the scalar perturbations. And this is certainly a challenge for many simple inflationary models. So this is taken from one of the Planck papers. So it shows you a whole bunch of models with monomial single field scalar potentials, which all fail to fit the data. There is one model that does fit the data, which is the Starobinsky model, and I'll be rabbiting on about that quite a lot in the coming minutes. It's not the only model that is consistent with the data, and actually the simplest possible supersymmetric model is also compatible with the data, as I'll discuss in a moment. So anyway, just to remind you about the Starobinsky model, so he wrote down this theory with an R squared term in the effective action. Doesn't look like it has a scalar field. How do you do inflation? Well, the answer is that you can do a conformal transformation, and in that way you recover a scalar field, and that scalar field has a potential which, when you calculate the density perturbations, as was done first off by Mukhanov and Chebysov a long, long time ago, then you get a small value for the tensor to scalar ratio, which is consistent, as I mentioned, with the Planck data. Now, that's not the only model which is compatible with the Planck data. And it was pointed out a few years ago by Bezukov and Shaposhnikov that you could also get very similar, basically identical predictions with the Higgs boson. And this would be a wonderful theory. This would be truly Occam's razor, rules okay. You put in a standard model, give the Higgs boson a non-minimal coupling to gravity, which is characterized by this parameter psi up here. You have to choose a rather large value of this non-minimal coupling. And when we talk about non-minimal, we're talking very non-minimal, okay? But anyway, then you do the calculation and you get an effective potential which looks very similar to the Starobinsky model. Not quite the same, somewhat different, but very similar. And to get successful inflation, you need a very large value for this parameter psi up there. So this is showing you what's going on. So the stuff that Lars was talking about, the stuff that's been verified experimentally, is this little invisible bit down here, okay? But the idea is that you run the theory up to high energies and you get a potential which looks rather like that, and that then gives you this green prediction for the inflationary observables, a value of the tilt and a value of R, which are, as I said, basically indistinguishable from the Starobinsky model. There's just one small problem with this. And the small problem is that you need that potential to be positive, right? And unfortunately, if you take the measurement of the Higgs mass that has been done by the LHC experiments and the value of the top quark mass, as I discussed earlier on, actually the potential is not positive when you go to large field values. It's actually negative. That is the instability that I mentioned earlier on. Now, I should say that this is not a definitive conclusion. In particular, it depends on the precise value of the top quark mass. And I emphasize to my experimental colleagues that it would be really, really, really nice to measure the top quark mass somewhat better than has been done so far, to really pin down whether this Occam's razor scenario is feasible or not. Okay. So Higgs inflation would be great, but to me it looks like no banana. So what else could you do with a simple scalar field model? Well, models with a monomial potential don't work out, but you could of course try a polynomial potential. And this is an example of a potential which does just fine, got a double well, gives you a better tensor to scalar ratio, and you get good inflation if you start off the field in this region down here in between the two wells of the potential. Okay, so you can do that, although at this stage it looks like a rather arbitrary model. Now, I was mentioning earlier supersymmetry. So I would actually argue that inflation cries out for supersymmetry. In fact, we wrote a paper with precisely that title back in 1983. The point is that these simple inflationary models involve what at least looks like an elementary scalar field. And in order to get the right magnitude of perturbations, you need either a mass which is much smaller than m Planck, so quote unquote unnaturally small, or you need a coupling which is very, very small. And both of these things look rather bizarre in a generic field theory. On the other hand, they would be technically natural in the framework of supersymmetry. So let's look at the simplest possible supersymmetric model, Westerminer model, written down in 1973. 2 parameters, a single complex scalar field. This is the simplest possible supersymmetric theory you could imagine writing down. And you calculate the effective potential, and it turns out that this model gives you good inflation. It reduces to the polynomial double well single field model that I showed you a moment ago, and in that region of the parameter space here, you get good inflation compatible with the Planck data. So here again is the Planck constraint on the tilt and the tensor to scalar ratio, and here's a bunch of models that don't do too well, and the Westerminer model, at least for certain suitably chosen values of the parameters, comes within this dark blue Planck-friendly region. So I'm not going to go through this in great detail. That was just for memory to say that there are parameters where this simplest possible supersymmetric model gives you successful inflation. But that's bullshit. You couldn't possibly take this seriously because, if you're talking about early universe, you have to worry about gravity. You can't muck around with a globally supersymmetric theory. You have to do a locally supersymmetric theory. In other words, you have to do a supergravity theory. Well, that's all well and fine, except that theorists have been worrying for 30 years about the fact that a generic supergravity theory doesn't look like it's tailor-made for inflation. It tends to give you a potential with big bumps and dips in it. In fact, generic supergravity theory even has holes in the potential with a value of minus m Planck to the 4th, which would really worry your grandmother about falling into it. However, that said, there is actually one exception. There's a class of theories called no-scale supergravity, which are actually generic in compactifications of string theory, which give you a nice flat potential with at least some control over the corrections to the inflationary potential. So we sat down back in May and tried to figure out, well, could you actually construct a no-scale supergravity inflationary model which would be compatible with the Planck data? So we looked at the simplest possible example, Westerminer superpotential, and hey presto, we found good inflation. So I don't think that for this audience I'm going to go through the details. I can assure you there are details. You could perhaps imagine that in the context of supergravity there are going to be details. But anyway, the thing works, and we got an effective potential which looks like this. So these various different colors correspond to different values of the parameters. And there's a black one here, which gives you a nice flat potential. The other ones, well, they're almost as flat, but not quite as flat, and they go up and they go down, and so on and so forth. So we were sort of looking at this, and my collaborator, Keith Olive, said, holy shit, or words to that effect. He said, this black one looks kind of like the Starobinsky model. And indeed, it is the Starobinsky model. So This again is the Starobinsky model, and I told you make a conformal transformation, you get an effective potential which has an asymptotic constant with an approach which is exponentially suppressed. And that actually is identical with this no-scale supergravity model, at least for one particular choice of the parameters. So I don't know whether there is some profound connection between higher derivative gravity and no-scale supergravity. I mean, we've written a couple of papers on this, and there certainly do seem to be some reasons for thinking there is some connection, although I don't think that we've really put our finger on the deep connection that must surely exist. So coming back yet again to the Planck measurements, this is actually showing in detail what this type of inflation model predicts. So, horizontal axis again, the tilt, vertical axis, the tensor to a scalar ratio. This is a blow-up of the region of interest. And the thing which is interesting about this model is that actually it doesn't, I mean, the black thing, that actually is Starobinsky, but it gives you other models which could give you a slightly different value of the tilt, slightly different value maybe of the tensor to scalar ratio. So it's actually something where you could sort of parameterize a space around Starobinsky, and then you could use experiment to distinguish what's going on. So it looks like the R-square model, but also allows possibilities for deviations. And I've been very glad to hear that there is, I mean, people were talking about long-term future in particle physics. Long-term future in CMB physics might be the somewhat unfortunately named PRISM project. But this would have sensitivity to the tensor to scalar ratio, which should get you, down below this prediction of Starobinsky et al. So there's quite a lot of theoretical activity in this area, and I just list here some of the recent papers on this subject. In particular, it was taken up shortly after our paper by Yanagida collaborators, Kalosh, Linda, and a whole bunch of other people. So in fact, there are generalizations of this model, a lot of generalizations, which again I'm not going to go through in great detail. Let me just show you this, which is, well, actually, maybe just focus on the picture on the right. The picture on the right is sort of interesting. It looks rather like this canyon that they just discovered underneath the Greenland ice sheet. But actually, this shows you that you can construct a complete model where you get good inflation. That Starobinsky model corresponds to coming out along this valley and coming down to the bottom here. But the other degrees of freedom that you have in the model are stabilized, and everything is tickety-boo. So I said that in this type of theory, you can construct extensions or generalizations of the Starobinsky model. And this is something that Benata Kalosh and Andrea Linde have also looked at. You can consider a general set of models where you have an asymptotically constant potential, which is approached exponentially, and then you can calculate the traditional CMB observables in terms of these parameters. And so you could imagine doing some sort of phenomenology of this. And in fact, in the sort of no-scale supergravity models that we're discussing, there's actually a quite generic alternative prediction, which would be somewhat different from Starobinsky, which would actually give you a somewhat lower value of the tensor to scalar ratio. So CMB might actually be a way of doing the phenomenology of string compactifications. I don't know if there's any string theorists here. So that brings me to the end of what I wanted to say. The discovery of the, or at least a, Higgs boson at the LHC has made scalar particles finally experimentally respectable. But I would argue that for these things to be theoretically respectable, you need supersymmetry. And of course, if you've got one scalar particle, you may have a whole lot more, In particular, you might have the inflaton. Of course, the Higgs boson might still be the inflaton, although, as I said, this looks a little bit unlikely. In fact, I would argue that inflation cries out for supersymmetry, and you can certainly make supersymmetric models that are compatible with Planck et al., and many of those models actually give something which looks very much like the Starobinsky model, and by probing, e.g. with PRISM, you might get a window on string compactification. Thank you.
Okay, questions?
I mean, the connection to fundamental inflationary theory are all based on measurement of NS and R, which are two numbers. And of course, we can expand any inflationary in slow roll parameters. And a large number, I don't even know what the number is, can cover quite a range of slow roll space. So how would you know, even if PRISM were to find an R of whatever 10 minus 3 and an NS of 0.97, that this in fact does connect to a specific theory as opposed to any other of large number of theories which can hit that same parameter space?
Yeah. Well, of course, you can never prove that a theory is right because there's so many theories. Okay. What you can do is prove that a theory is wrong. Right. So, I mean, the Starobinsky model makes very precise predictions as to what NS and R should be, and this can be disproven, right, which would certainly be something useful to do. And as I mentioned, the other models, the generalizations that I discussed, these can also be disproved.
So you gave us a sense of Starobinsky-like models and supersymmetry and so on. Is there enough structure in these models that would tell us what the couplings would be to Simon model fields and so on? So you could do reheatings and something like that in these models?
So the Starobinsky model per se, doesn't say anything about that. The sort of class of models that I discussed, yes, then you could start doing some more specific phenomenology, and perhaps this would have been a better answer to your question, because then you can relate to it to other observables. And the precise way in which, in our model, the supergravity degrees of freedom are connected to the standard model degrees of freedom would affect things like, for example, the reheating temperature, which would in turn play back into the precise prediction for NS, right, which, as you know, is sensitive to the amount of e-folds that you have. So that is something which we're working on at the moment.
So baryogenesis requires physics beyond the standard model. And I guess one of the numbers we've measured with precision in cosmology that particle physicists haven't used yet is the baryon-photon ratio. The fact that you need to have new physics, what does that mean for things like the stability of the vacuum? I mean, there's got to be something there beyond what we see, beyond the single Higgs.
Right. So I would argue that in a generic supersymmetric theory, you stabilize the vacuum. Okay. Right. When you go to a generic supergravity theory, the problem comes back in spades. But no scale supergravity at least provides a palliative for that problem. So that's part of the whole sort of background of why I'm heading off in this direction. Now, with regard to the point about baryogenesis, amusingly, in this scenario, the field that drives inflation could actually be responsible for baryogenesis. And that would actually be the simplest example of sort of connecting to reality, so to speak. And so that scalar field that I had, complex scalar field, could actually be the supersymmetric partner of a neutrino, which when it decays could then give you baryogenesis. And so you get, everything done in one package, which at least would have the merit that it could be disproved.
Thank you very much for a wonderful talk. Can I just ask, for people outside of particle physics, it's a perfect example of we're always struck by the contrast between the theoreticians who have, such a strong motivation for supersymmetry. All of the arguments you presented are very convincing, and yet at the same time we always have the experimentalists talking about how they can't see a shred of evidence, and again we hear these talks. Yeah, I mean, given that it took that long, that long for the Higgs. I mean, I suppose one must have to sort of contemplate the idea that the first, I like the word yet, but let's imagine that the first supersymmetric particle turns out to be extremely difficult to find. And this comes back to the first question. I mean, it seems to me that anything that comes out of the CMB will be, shall we say, not incompatible with, rather than direct evidence. That the problem is, how does one, what happens if it takes an extremely long time to find a particle at the LHC?
Yeah, so let me just retaliate with a little bit of history. So as I said, the Higgs boson was postulated in 1964 and was discovered in 2012, 48 years. So supersymmetry was postulated in 1973. Hey, come on, guys, it's only 40 years since supersymmetry was postulated. So, give the LHC, 8 years to look for supersymmetry, and if it doesn't find it within that period, then I'll be retired.
Okay, one last question.
But seriously, though, folks, I mean, in addition to the LHC, we've got the dark matter searches, and I guess that Malcolm will talk to you about that. Those are going to certainly be improving in the coming 8 years, too.
Cliff?
This is just a comment. I like very much the emphasis on the exponential potentials as opposed to the curvature squared models. And I just wanted to comment that there's a motivation for having those kind of no-scale models coming out of string inflation. 5 or 6 years ago, fiber inflation kind of models tended to give you that kind of generically give you that kind of a structure when the inflaton was a modulus. There's a general argument why you're getting exponentials in the potential if it's a modulus.
Right. So in our framework, this field could actually be a modulus, or it could be a matter field which is sort of linked together with a modulus in some sort of no-scale structure. So I think this is a very interesting region of theory space to explore.
Okay, so before we thank John again, I just have 2 quick announcements. The first one is that if you haven't signed up for the banquet yet, it's not too late, so you can go to the reception and get a ticket for that. Also, if you want to go to the public lecture and don't have a ticket, you can still get that. And then finally, if you're giving a talk in a parallel session today, it's important that we get your talks, and slides in particular. So please go upstairs to the reception desk. There will be USB sticks. It's a 2-step process. The first step is you find the session number. There are 3 sessions this afternoon, and then you put your talk on a stick labeled 1, 2, or 3, depending on which number session you're in. So, and we're going to be upstairs to help with that process. Okay, thank you very much, and thanks to John again for a nice talk.